All right, chapter 21, aldehydes and ketones. Let's go through some of the basic stuff, the real easy stuff to begin with. First of all, if we have a ketone versus an aldehyde versus two hydrogens on the carbonyl-carbon aldehyde, we see that aldehydes are more reactive than ketones. This is due to two reasons. Reason number one, steric hindrance. R groups are larger than hydrogen. So the more R groups we have on there, the more sterically hindered that carbonyl carbon is, the less reactive it is. Also, note that R groups are slightly electron donating. Alkyl groups are a little electron donating, which means they're going to donate a little bit of their electron density to that carbonyl carbon, which means that carbonyl carbon has slightly less positive charge than this carbonyl carbon. And this carbonyl carbon has less positive charge than that one. The less positive charge you have, the less likely a carbonyl carbon is to be attacked, because nucleophiles, negative things, want more positive charge. Two R groups donating electron density to this carbon, there's going to be less partial positive charge on this carbon compared to this one over here, which means less reactive. Okay, nomenclature. IUPAC wants to end the molecule in Al, Al, excuse me. So when we look at this one right here, very straightforward. Carbon number one is always the carbonyl carbon of the aldehyde. Note the aldehyde ends the molecule. That carbonyl carbon is the last one in the chain. Well, let's call it the other way. Let's always say the carbonyl carbon is the first one in the chain. So this is carbon number 1, 2, 3, 4. Note 1, 2, 3, 4 carbons in the chain, including the carbonyl carbon. Therefore, 4-carbon chain is a but, or a butane. Since it's an aldehyde, it will be a butanal. And we have methyl groups on carbon 1, carbon 2, and carbon 3. So 2,3-dimethyl butanal would be the IUPAC name for it. The common names for these, you gotta like it. We just end it in the word aldehyde. Recall CH double bond O, HC double bond O is the form group. So if we have this part right here, C double bond OH is the aldehyde, HC double bond O is the form group. This is formaldehyde. Recall, if we see this, okay, C double bond OH is the acid group. C double bond OH is the aldehyde group. CH3 C double bond O is the acid group. This is acetaldehyde. Okay. And note that, as we saw before, with naming it using the common names, the carbonyl carbon is here. The one next to it is alpha. The one next to that is beta, gamma, delta, etc. So if we were looking at this, 4 carbons in your chain, including the carbonyl carbon, that's a butyr. Actually, no, 1, 2, 3, that's the propion aldehyde. So this would be a propion aldehyde, and this would be alpha beta dimethyl propion aldehyde. All right. Naming ketones. IUPAC, okay job. If you have CH3, C double bond O, CH2, CH3, IUPAC says, okay, 4 carbons in the chain, that's a but. The functional group is a ketone, so that's a butanone. We need to indicate which carbon is containing the carbonyl carbon. So that's carbon 2 in the chain. This is 2-butanone. Note, you cannot have 1 butanone. Tell me, why can you not have 1 butanone? Because if it was 1 butanone, that would mean the carbonyl carbon was on carbon number 1, and it would not be a ketone. It would be an aldehyde if the carbonyl carbon was the first carbon. So there's no such beast as 1 butanone. All right. I really like the way the common nomenclature system names your ketones. It's so nice. You just say, okay, what's on this side? Well, here's our carbonyl carbon, that's a methyl. What's on this side? Oh, that's an ethyl. What comes first alphabetically? E for ethyl, so this will be ethyl methyl ketone. There's so little thinking involved with the common way of naming it. It's just so nice. I've got a ketone, ethyl on one side, a methyl on the other. Let's call it ethyl methyl ketone. Yay, I like that. If you have double bonds and carbonyls, you can have an enal or an enone. All right, little spectroscopy. Recall with IR, aldehyde has these two kind of like fangs at like 2813, 2716, around there. They tend to be fairly prominent peaks. Note, if you ever see a peak at like around 2750 or less, look for a peak about 2850. And if you see both and a carbonyl peak, then you're pretty much guaranteed there's an aldehyde in there. Note, a lot of times people will see like a 2850 and a 2950 and say, oh, aldehyde. No, no, no. It's got to be 27 less than 2750 and 20 less than 2850 for it to be the aldehyde. All right. Also remember with the Proton Nmr that the aldehyde hydrogen comes around 10, 11 ppm, and it's on a carbon. So this proton will be split into a triplet by these two protons here, because there are two protons on the carbon next door to the carbon containing that hydrogen. One thing about it though, the coupling constant for this triplet is small. It's a 1 to 3 hertz J coupling, which means it's going to be really skinny, a really tight together triplet. Okay, next page. Let's look at some general reactions of aldehydes and ketones, and we've kind of seen these before. Before we add a carbonyl carbon, we have a nucleophile. Nucleophile will attack the carbonyl carbon. Aqueous workup turns it into an alcohol. What we're going to spend a lot of time with in this chapter, because it's really cool, is looking at the alpha carbon. It turns out if you have a carbonyl and you have a CH2 next to the carbonyl, or a CH, these two, or this hydrogen here, is actually more acidic than you think it would be. And a base can come along and take that hydrogen to make this carbanion. And why would it do that? Well, this carbanion is in resonance with this oxoanion here. And what do we know about resonance? If the product of the reaction has resonance, that means the product is more stable than you'd think it would be, which means this reaction goes further to the right than you think it would be. Normally you wouldn't think that a base would take that hydrogen due to pKa values, but due to resonance we're going to find out the pKa of this hydrogen is much lower than you think it would be. And once you have a negative charge on here, if you add an electrophile, note what's more nucleophilic, O- or C-? Answer is carbons are more nucleophilic than oxygens when they're negative charge. Carbanions are extremely strong bases. Carbanions are stronger bases than alkoxides. So if you have an electrophile, something positive for the negative to attack, it's the carbon. The carbanion is a more nucleophilic beast, and it will attack that electrophile. The electrophile will get added to the alpha carbon. All right. There are a couple ways to do these reactions. Note, if you're under basic conditions, if you have a strong neutral or a negatively charged nucleophile, the nucleophile will attack the carbonyl carbon first. Lone pair, or the pi bond will break, putting a lone pair up on this oxygen, make it negative charge. Aqueous workup means we protonate that, and we get the alcohol with a strong nucleophile. The nucleophile attacks, then we get the protonation. If we have a really normal neutral nucleophile or a weak nucleophile, we find that weak nucleophiles do not like to attack carbonyl carbons very readily. a weak nucleophile, just not very negative, and the carbonyl carbon is just not positive enough. How do we make it more positive? We throw in some acid. So if we have a really weak nucleophile, we need to throw in an acid. The oxygen will attack the hydrogen of the acid to protonate it. Resonance means that the positive charge that is on here can get transferred down to the carbonyl carbon. So note that this carbonyl carbon, due to our carbonyl attacking that acid, our carbonyl carbon now carries more positive charge. Since our carbonyl carbon has more positive charge now than it did before, now a neutral nucleophile is like, okay, I'm all up in that, and I will attack that carbonyl carbon. And so the nucleophile attacks, and then our conjugate base of our acid, A- comes in, deprotonates that nucleophile to regenerate HA again, which means our acid is a catalyst. And so here we have protonation first, then nucleophilic attack. All right. And the last thing we're going to look at in this video is making a cyanohydrin. Recall, cyanide is a very good nucleophile. So, if you have cyanide in here, the cyanide will attack the carbonyl carbon. Throw in some HCl and we will get this beast right here. Note the HCl has to come in second. Don't put in cyanide with HCl. You'll generate HCN gas, hydrogen cyanide, and you breathe it in and you die. So don't do that. Put in the NaCN, let that reaction run. Then put in HCl for protonation. The carbonyl oxygen becomes the OH. We get the cyanide on what was a carbonyl carbon. And well, now we have the cyano group on here. This is, or a nitrile, as we call it, a cyanohydrin. And what can we do with these nitriles? Well, we can do aqueous, or we can do hydrolysis, either in aqueous acid or base. And we note that nitriles with hydrolysis become carboxylic acids.